is Professor John Abatzoglou. John Abatzoglou is Professor of Climatology and also Professor of the Management of Complex Systems at the University of California, Merced. He teaches environmental systems science, climate hydrology, applied climatology, and does research. He received his BA, his BS in atmospheric science from UC Davis, and his doctorate in earth systems science from UC Irvine. His interests are primarily focused on climate science and impacts in the American West. He has a climatology lab that develops data sets, include, for example, GridMet or SlowClim, which are physics-based snow models measuring snowpack and variability. So his climatology lab focuses on climate science, meteorology, and their impacts on systems like water resources, wildfire, and agriculture. Professor Abatzoglou is a prolific scholar with a rich peer-reviewed practice. He has co-authored 221 refereed publications just last year, 15 publications, and he's also a journal reviewer for many peer-reviewed journals. He also presents to the public. The past year, he presented to the California Water Commission on the drought, and the Insurance Institute for Business and Home Safety Disaster Dynamics Academy on fire activity. In 2015, he was awarded the International Journal of Climatology Prize, and he's given 50 to 60 interviews a year to publications like the LA Times, New York Times, NPR, Seattle Times, Scientific American, The Atlantic, and many others. Please give a warm welcome to Dr. Abatzoglou.
Well, thank you for that introduction. And thanks everybody for showing up. You have a lot of options on a Friday evening, and I know, what was it, 60% here for extra credit? But probably that same 60% is really interested in weather and climate, right? We have certainly seen a lot of weather and climate in the news here in California. Just within the Central Valley, right, we had towns approaching day zero water, right, at the end of last year. And then we had towns underwater within the last few weeks, right? And part of this is the story of California. This is a state where water is hugely important, but we have massive variability, right? We cannot never count on average in terms of water resources here in the state. However, we have seen more variability in recent years. We've seen droughts that are unparalleled to droughts that we've seen in the observational record, and even droughts that we've seen in the last 1,200 years. California is also a really interesting state because if you think about the state of California, we have huge variability in climate spatially, right? Along the northwestern coast, we have the redwood forests. In the Sierra Nevada, we have areas that might only see a month or two of snow-free conditions. The coastal strip of Southern California, to many, is the Shangri-La of climate. It is perfecto, right? 72 every day, more or less. We have the super hot and arid deserts in the southeastern part of the state. And then here in the Central Valley, we have a semi-arid climate. We benefit from having rich soils. We benefit from having snow melt from the Sierra Nevada, and that allows us to actually cultivate some really high-value specialty crops. Now, all those things I mentioned there, as a climatologist, I'm biased, but I do believe that those things, climate, influences the resources that a region is based on, influences the culture and the identity of that area. So if you follow my argument there, if climate changes, those resources begin to change, and regions' identity and culture may change. So with my time here this evening, what I want to do is accomplish three things. We're going to go through sort of what the state is of climate change. And it looks like some of you have had a little bit of that, right? We'll get a little bit more here today. We'll talk about the impacts of climate change here in California, things that have already manifested themselves, things that may be coming down the pike. And rather than end there and leave everybody in a dour mood, we'll talk about optimism in ways in which we can begin to, and maybe already have, begin to slow down climate change and the impacts here. Okay, before we get going, because it's the evening, we're going to do a little exercise, right? And this exercise is the word analogy game, right? You've all probably seen this word analogy game in high school, right? Something is to something as something is to something, right? So weather, right? What is weather? Can you define weather? Anybody want to take a stab at defining weather?
The temperature outside.
Perfect. If you want to know the weather, go outside, take a measurement, the temperature. What's climate then? Take a lot of temperatures. For 30 years outside, get really bored, right? Climate is, to some degree, made up of lots of little weathers, right? It is the statistics of weather, right? With climate, we can tell you what we expect today to be like, but we can also tell you what the range of variability is. I like to think about climatology as meteorology with context. We had a series, in fact, 9 atmospheric rivers make landfall here in California, right? Each atmospheric river event was meteorology. We can contextualize that with climatology. And that much of the state saw basically its wettest 20-day period in a century, right, during that spell. Okay, you want to do the exercise? Should we skip it? We'll try it. Okay, so weather and climate, right? So if weather is your mood, then what is climate? Got some points. Okay. If weather is what you're wearing, style, wardrobe. And I don't wear this every day. I haven't worn, like I went in and I'm like, oh my God, that was from 2015. So if weather's what you have for breakfast, your diet, right? Right. What's in your fridge. Now, if you go on a diet, right? If you go on a diet, you switch from having bacon and eggs for breakfast to having oatmeal for breakfast, maybe for a reason. You may still occasionally have bacon and eggs for breakfast, but the frequency, right, and how much bacon you consume is going to be different. And so climate change does involve changes in the weather, okay? Statistics and changes in the weather. So let's go and talk a little bit about sort of what has happened so far and how it has impacted us here in the western United States, in California in particular. We've been collecting observations, right, thermometers. We've been taking measurements of temperature globally for some time. We don't have thermometers everywhere. It's not a perfect science. But we do have a reasonable degree of accuracy with understanding how the globe's temperature has changed through time. And these are annual temperatures. The data for 2022 was updated within the last few weeks. The story here, you don't have to know too much about statistics to realize that that line is going up. Right, we have seen warming globally of about, just over 1 or 1.2 degrees Celsius, right, or 2 degrees Fahrenheit over the past century. Most of that warming really has been since the 1970s or so. So, right, what's 2 degrees Fahrenheit? Doesn't sound like much. 2 degrees Fahrenheit, I mean, I think if we were to go outside and take the temperature right now, by the time we leave this session, it's going to be 2 degrees Fahrenheit colder outside. And certainly from day to day, temperatures change dramatically, more than 2 degrees Fahrenheit. So why do we care about 2 degrees Fahrenheit? Anybody have an idea? Or should we just go through this? It's too big of an audience, perhaps. So one reason is that we don't live on the globe, and it turns out that if you look at global warming, right, it is spatially variable. Land masses have warmed a lot more than the ocean has. And it turns out that, in California, the warming has been more on the order of 3, right, or 3.5 degrees Fahrenheit. Again, small number, but it's getting bigger. We also know that if we look at California, right, and this is a map of California, but it's showing us sort of the average high temperatures in summer, we know that there is a lot of variability within the state. Central Valley is pretty warm, but it could be hotter. So when you're complaining about the heat, look down to the southeastern deserts. We also know that it's quite cool in the mountains. and the coast. We experience this sort of spatial variability in climate, right? It's hard for us to sort of grasp what we mean when we're talking about a change or an increase in temperature of 3 to 4 degrees Fahrenheit over the past century. Okay, so globally 2 degrees Fahrenheit looks like a small number. Another reason why that matters is the warming that we see here globally, probably, I mean, to many people, right, the Hallmark Indicator, if you live in the West, the Hallmark Indicator of climate change that you see is the snow line moving uphill, right? And we know that snow falls, right, when the temperature is below freezing. Yeah, it can fall a little bit below the freezing level. But with the warming that we've seen, right, in the winter, when we have precipitation, now the snow level is substantially higher than it used to be, right? And roughly speaking, the warming we've seen has translated into about an 800-foot rise in that elevation band where snow is falling and transitioning into rain. And if you think about a mountain range like the Sierra Nevada, you have a lot of elevation down low, not so much up high. So what this has translated into, right, more precipitation falling as rain, less as snow, more of that snow melting earlier in the year, is widespread declines in mountain snowpack by spring. This year's different. The snowpack right now is absolutely exceptional, the highest it's been in at least the last 40 years for this date. Okay? But by and large, snowpack has trended downwards. So we have less snow. Here in California, we really, really, really depend on snow, right? Because we get precipitation in the winter, we use water in the summer. And so snow provides a conduit, right? It holds that water in a frozen form. It's our most important reservoir. It releases it as the temperature's warm in the spring, and then we are able to capture and use that water come the demand season for irrigation, right, for municipal water use. Unfortunately, right, as we have seen changes in climate, we have seen less snow and less flow, right? And this is looking at the state of California in terms of runoff, right? Measured runoff coming down our rivers. So less flow is not great. That's surface water supply that, of course, we use, and all of us here in the Central Valley know is critical for everything. We have run into the last 3 years up until, of course, this winter. Those are the 3 driest years the state has seen, at least the 3 driest consecutive years the state has seen in at least the last 120 years. Massive impacts in terms of agriculture and, to some degree, the economy. Okay. I'm rhyming here, by the way. Less snow, less flow, more fires grow. Stay with me. Okay. We have seen a significant uptick in fire activity, not only here in California, not only in the western United States, but in actually a lot of forested areas in the mid-latitudes, right? Canada is included in that. Australia is included in that. Here in California, in the western United States, hot, dry summers generally correspond to active fire seasons, and we've seen hotter and drier summers substantially over the last 30 to 40 years. The amount of fire on the landscape today dwarfs what we saw in the middle portion of the 20th century. And climate change, right, the warming we have seen and the drying we have seen has contributed and facilitated that. Okay, my rhyme here is quo, staying with it. Okay, and drought, right, I mean, I prepared these slides before the onslaught of rain, so that's okay. But drought has been the word that we have just referred to in California year after year after year. Occasionally we forget about it, but then it comes back, and it'll come back again, right? Looking at some of the historical data, because we only have rain gauges and thermometers really for the last 100, 150 years or so, but we also know that there's some really good recorders out there in the natural world. Tree rings, for example, are really good at recording moisture signals. Certain trees are really good at recording moisture signals. So we can use those trees and reconstruct climate going back further through time. And when we do that, we find that since the turn of the millennia, the broader southwestern United States is about as dry as it can get, right? We call this the mega drought, long-term chronic drought, right? That's the driest it's been in at least 1,000 years for the broader Southwest. Okay, and climate change is part of that as well. So the images that we sort of talk about, we're talking about climate impacts in California, a lot of them, at least for the last 10 years, have looked like the ones behind me here, right? But guess what? It does still rain, right? And when it rains, it pours. We know that. We have had 3 very wet years in the last decade. Otherwise, the years have been pretty darn dry. They've all been warm. And these are obviously scenes within the last month, right? Heavy precipitation events. It turns out that climate change can simultaneously increase the risk of drought and increase the risk of floods. Isn't that weird, right? It is hard to contextualize what drought means, but it effectively is a lack of water for resources, and those resources vary dramatically. What we do know about heavy precipitation events, like the atmospheric rivers that made landfall here in California, is that these sorts of heavy precipitation events tend to increase with warming globally. So rough estimate is that these precipitation events were probably 5 to 10% more intense than we would have seen in the absence of the warming climate. So what have we learned, right, just looking at some of the observational data? I mean, first and foremost is that we are sensitive to climate variability, right? I mean, that probably was pretty obvious to most people living in California. Other parts of the United States, they're beginning to realize that it might matter a little bit. The other thing, I think bullet point number 2 is maybe 5 or 10 years ago, if I was talking to audiences, I might have said we're looking at these sorts of changes materializing in the future. We're not waiting anymore. We're in the middle of it, right? My take here is that the climate change story is half written. We don't know how the second half is going to end, right? We're in the middle of it. These changes are now linked to human-caused climate change. Not every single weather event you see, right? But certain ones have already been linked. The good news, right, because there has to be some good news here, is that science can help inform policy and help create a more resilient society and potentially help slow down, right, and or reverse what's happening. And this is what science is, right? So as a scientist, there's things I know and things I don't know, and there's things I'm never going to know. Science is a puzzle. It's a puzzle that never actually gets completed. And the goal of science is to try to fill in pieces of this puzzle, right? And so as time progresses, right, we're going to fill in bits and pieces of the puzzle. Science is also open to correction. We could go back and take a puzzle piece going, that didn't belong there, let's move it over here. Science is never going to be completely solved, right? And this is kind of where we are with climate change, right? We know the big picture. We may not know all of the little details, but it's a bowl of fruit, right? It's a bowl of fruit. I don't know how many grapes are up in that upper left-hand corner, but there's some grapes there. So we have the information today, even though we're going to learn more moving forward, we have a lot of information today to understand what is going on and to understand what we might be able to do about it. Okay, so I'm going to give you just a few quick slides here on the basic science behind human-caused climate change. It looks like maybe over half the people here have had 30 minutes or less. So again, we're going to double that today. So there are 3 main things that control the global thermostat, what the temperature of the planet is. Anybody want to guess one of them? Greenhouse gases. So carbon dioxide is one of them. Water vapor is the biggest greenhouse gas. Anyone want to guess another one besides greenhouse gases?
Forests?
What's
Trees?
Trees?
Plants?
Plants could be. So plants do a couple things, right? They take up carbon dioxide. Oceans do stuff. So plants and oceans actually color the planet. The reflectivity, so the reflectivity of the planet as well as clouds, those are going to act to reflect the amount of solar radiation. We know that it's hotter in the daytime than at night. It's because solar radiation's out, right? And then the last piece is solar radiation, right? The sun can change through time as well. So those are the 3 main things that influence global climate, right? It's the sun, right? It's the color of the planet, the Earth's surface, or cloud cover, or aerosols, right? Reflective matter. and then the Earth's atmosphere, really speaking here specifically about greenhouse gas concentrations. Okay? Humans have influenced 2 of these, right? Not the sun, at least to my knowledge. We've been measuring the sun for quite some time. Some people have gone blind looking at the sun. Their job was to count sunspots. Stay in college, don't go. That's not a good job. We have some better instruments now. The Earth's surface has changed. For example, in urban environments, we have changed the land cover there. Right? Urban environments tend to be warmer than non-urban environments. In the Central Valley of California, we have 7.5 million acres of irrigated lands. That actually cools the climate. It uses a ton of water, but it cools the climate specifically in summer, okay? Especially in the daytime. And then, of course, greenhouse gases, that is ubiquitous. That is a global phenomenon. Couple more complicated figures. Right? This figure here is from a big synthesis that comes together. Scientists from around the world come together and they synthesize the state of the science. It is a complicated process, come up with a report every 7 years or so. What I am showing you here is just how much of an impact different factors such as carbon dioxide, other greenhouse gases have influenced not the temperature of the planet, but how much energy the planet is retaining or trapping, right? The additional energy. And the big take-home message here is that some people say it's the sun, right? The sun is responsible for the warming we've seen, and you can see solar at the very, very bottom here. It's essentially negligible, right? So solar activity has not really done anything. The big drivers, at least in terms of the changes we have seen, are highlighted in red, right? And that is the increases in greenhouse gases. It turns out that all the pollution that we see, right, the air quality issues, things that we see visibly in the sky here in the Central Valley, especially in the winter when we have inversions, right, that sort of matter ends up actually cooling us just a smidge. It's not good, but it does cool us a bit. Okay. So there's more to the story, right? There's lots of ways to understand climate change and climate science. And I will say that I come from a background where my goal in life as a little kid was to be a weather forecaster. And then I went to UC Davis in the meteorology program, and I was terrible. I was second worst in the class. All the other students went on to work for the Weather Service, and I was like, I need to get another degree. But in doing so, what I've understood along the way is that there's lots of different fields that are working on climate change today. More and more, I see people from sort of soil science and ecology, right, contributing to climate change. We have the social science and humanity also contributing to the climate change problems and how we solve them. So climate change is not just about the atmosphere, right? It's actually about how all of these fields come together. And climate models, right, it sounds a little dorky and geeky, it is, right? These models are run on some of the most impressive supercomputers globally, but it actually takes a field of researchers that work on the atmosphere and the ocean and plants, right? How all these things interact with one another, okay? Models are really important when it comes to climate change. If you're in the field of biology and you want to test out whether a new drug is effective at curing a virus, for example, you can do that by testing it out on a lot of lab rats, for example. You give half of them the drug and half of them the placebo, and you do statistics on that. We can't do that with climate. We have one planet. We've already performed experiments on it. We don't want to find too many other experiments. We don't want to find too many planets to do experiments on. So that's why we have to use models to do this. And models, right, are pretty complex. You use models all the time, whether you know it or not. When you look at your phone and you look at what the weather forecast is, that weather forecast is giving you information that's coming from a numerical weather forecast model. Yes, that model could be wrong sometimes, but it probably influences what you do. It probably saves you money, and it certainly saves a lot of lives as well. Okay, so the same sort of model information we can use when it comes to global climate change. We're just looking at really, really long time scales. Okay. So I'm going to show you, again, one or two more slides from sort of the global climate change science, right? We can use these models to test out hypotheses, right? That's sort of one of the tenets of the scientific method. Form a question, test a hypothesis, right? Confirm whether the hypothesis is true or not. So these models, we can actually run them with the different scenarios, right? One scenario, for example, is we're going to run them over the period from 1850 to 2020, but we're only going to consider natural climate variability. Things like known solar cycles, things like large volcanic eruptions. And when we do that, we get the green bar, the green lines, which effectively show no significant change through time. The other experiment is we're now going to add in all of the human-caused factors, right? So that is the greenhouse gas emissions. That is the aerosols. And when you do that, you get the second set, the gold line, and you can see that that matches fairly well with the black line, which is observations. So experiments like this, modeling experiments like this, along with observations, along with theory, right, in terms of how greenhouse gases should effectively increase the Earth's surface temperature, allow the large scientific body to make a definitive statement that humans are the primary cause of observed changes in the global climate system over the past 50 years. Okay. There's uncertainty within that, but you can kind of see that from the figure here. Okay. So like I said, we've written the first half of the story of climate change. The second half isn't written. We're all going to play a role in shaping the second half of this story. Things are looking like temperatures are going up. Question is how high they will go, right? And of course, it's not just about temperature. We care about things that are more tractable, right? Here, we care a lot about water resources, I would say. Water seems to be a metric that is pretty essential for life, so it makes a lot of sense. So where are we going to go? Well, the bottom line is that most of the changes in climate we've seen so far have been tracked to human-caused greenhouse gas emissions. The story on emissions, right, is depicted behind me here. A little hard to see perhaps, but emissions have increased, and certainly up through around 2010 or 2012 or so, things were looking pretty bad, right? That curve was looking pretty bad, a pretty steep rise. Things have maybe begun to bend the curve a little bit. Certainly you can see the dip in 2020. The bad news is that that dip was temporary. And in 2022, the estimate is that the human-caused emissions of greenhouse gases were their highest on record. Okay. Look a little bit at the curve, possibly. Our goal here, if we want to reduce the pace of human-caused climate change, is not just to flatten this curve out, right? Because these are emissions. And if the analogy here is that it's like you have a bathtub, and the bathtub is the bathtub is rising with water. You have a little bit of a spigot, so a little bit of water is running out the bathtub, but the amount of water being put into the bathtub exceeds the amount that's draining, and so your levels will continue to rise. What we actually need to do is bend this curve so that emissions start going down, right? That would be a desirable goal for some of what we call the mitigation plans. Okay, so the future, again, is not written. There's uncertainty with respect to these 5 things here. None of the 5 I'm an expert on, but they're worth highlighting, right? How we're going to use energy, how we're going to share technology, how economies will grow, right? Population growth, of course. And then that bottom one there is carbon sequestration. Because if we can't slow down the rate at which we're putting carbon into the atmosphere, well, then we've got to figure out a way to take carbon out of the atmosphere at a pretty accelerated rate. Okay. I want to spend a little bit of time talking about what the future looks like in California. And I've got an example here for Modesto. I want you to think about where you might find the climate of Modesto in 2050. Where might you go today to find that climate? So think about that while I sort of go through a couple slides here. Like I said, California has warmed 3 to 4 degrees Fahrenheit over the past century or so. Where are we going? It depends, right? It depends on sort of how much carbon we put up into the atmosphere. And so the scenarios are that we're going to warm, right? Unless something significant happens in terms of mitigation. My group has run suites and suites of models, and we've developed a suite of tools as well to help inform how people use and incorporate climate information in planning and science. So this is a snapshot here for Modesto, and basically, if we slow down the rate of climate change and begin to reduce emissions within the next 20 years or so, and then significantly reduce them by 2080, we'll follow this blue line here, right? And that's, I would say that we could be on that trajectory, right? If we continue to do what we've been doing so far and don't ramp things up substantially. That still results in about a 4 degree Fahrenheit worth of warming, right? Which would make Modesto probably feel a little bit more like Fresno or Bakersfield temperature-wise. I live in Fresno, it's okay. The other scenario here is we embrace coal. We go back to embracing coal, and we rely primarily on fossil fuels like we were doing, up to 2010. Okay? I don't know if that scenario is likely anymore. There is enough carbon in extractable fossil fuel reserves to do that. And political changes could potentially allow for that trajectory. That trajectory would result in a warming of 8 degrees Fahrenheit, which is not pretty. Not pretty. I don't even know where that would go. We would have to go into the Sonoran Desert for you all here. We don't want to do that. Okay. Beyond temperature, we have seen a lot of drought here. We expect more drought. We expect that the risk of drought will increase dramatically, right? In a normal sort of stationary or non-changing climate, drought happens so often, right? In a changing climate, what we expect is that we will have warming. A warming climate results in a thirstier atmosphere that draws more moisture away from the surface, drawing out your soils, drawing out your trees, creating thirstier crops. That's kind of what we've seen, right? Creates a whole suite of problems. One thing that we do expect with climate change is a much greater increase in long-term droughts, kind of like the mega drought that we're in right now. Okay? And again, right, I'm telling you that we could have a mega drought. We're in one now. It's more likely in the future. At the same time, right, with a warmer atmosphere, an atmosphere that can hold more water vapor, you can get significant increases in heavy precipitation events. How many people have heard of the arc storm? A few people. So this arc storm was the idea that you had 40 days and 40 nights of rain here in California. The Central Valley was flooded. I don't know what happened in Modesto, but I think in Sacramento, I know they had to relocate the capital. We had this massive amount of water coming down. The 3 weeks of precipitation that we had here in California, we would have needed another 2 weeks on top of that and slightly wetter to have matched this arc storm that happened in 1962. That is evident in the historical record of California. We see that in sediment records. About every 200 years, crazy stuff happens. The issue, though, is that with climate change, that becomes much more likely. And this is a study here that effectively says, if you just track this, effectively, do I want to push the red button? It's going to be dangerous. Oh, there we go. No. Well, effectively, you can see here that the odds of such an event as you warm the planet up by 2 degrees Celsius, it's effectively twice or 3 times what it would have been. Okay? So that may not mean that you're going to get an arc storm like this every year, but you are absolutely loading the dice for an event like this to come around. And we have seen here in California, I think the number is something like 20 to 25 people died as a result of this series of events. The initial estimates are something like $7 billion of economic damage. That is a big impact, right? And then, of course, we've seen the side of fires and the impact that fires have had on life and the impact that fires have had on economics and community. Okay, so if the world reaches 2 degrees Celsius above its pre-industrial climate, which is approximately another 1.5 degrees Fahrenheit worth of warming, where would you end up having to go to find a climate similar to what you'd find in Modesto then? Where would you have to go today to find that climate? The answer's up here. I should have prepped it a little bit. Basically, you would have to find a similar climate in terms of temperature and moisture, seasonal availability of moisture. You'd have to go over to the west side of the valley, right? Which is, it's drier, right? If you look at the environment over there, it is drier, right? Certainly there's some groundwater issues associated with that, but this is a drier climate. It is slightly warmer as well. These sorts of changes in climate might be one way of thinking about climate change beyond just a number, because a lot of people, I think, are not able to react to if the world warms by 2 degrees Celsius, so what? Let's take you there and show you what this looks like. Okay. So I want to move over to the solution side and talk about what can we do. How can we change possibly this second sort of chapter on climate change? Well, admit there's a problem, and it looks like, I mean, the survey that Bill put up earlier, I think 90% of you said that humans are primarily responsible for climate change. I used to teach at the University of Idaho, and I would ask that same question to my students, and it was always 50-50. So we have some sort of change here. I think that's good. So you're admitting there's a problem, good. And maybe even responsibility for the problem, maybe better. 2 is to act, right? And so there's 2 things I'll highlight here, and I'll give just some small examples, right? 1 is to adapt. So that is that we're going to actually prepare for climate change. We're going to try to minimize the impact that climate change has on things that we care about. Okay? To some degree, that's how humans have existed through time. We're more adaptive today to climate variability and change than we were 100 years ago, right? We have invested in technologies. Some of those have worked, some of those haven't, but the reality is that we have done adaptation. We can do more, and instead of adapting to what has happened in the past, we adapt to what we think is going to happen in the future. Okay? The other one is to mitigate, which is to actually take action to slow down or stop climate change, which is through the carbon cycle, right? Emitting less carbon into the atmosphere, sucking it out of the atmosphere. Bring down the amount of carbon dioxide in the atmosphere. Okay? That's a hard one to do, especially if you do it by yourself. We can all do that by ourselves, but we are 1 out of 8 billion people now, right? 1 out of 8 billion. So that becomes hard to do without cooperation, without government stepping in and trying to actually make this a significant effort and priority. Okay, so adaptation I talked about already, right? We're trying to avoid harm. There's ways to do that, right? The nice thing about adaptation is that it can be done locally. The bad thing about adaptation is that it requires money to do. So adaptation is happening here in California, and it turns out that affluent communities are doing adaptation first. Okay, sort of the communities that do not have money are being left out to dry, and that also is showing up globally, right? Some of the areas that are being most impacted by climate change do not have the resources to adapt. Part of the big sort of governmental policy on climate change is to actually provide resources from first world countries to help third world countries adapt to climate change. Okay. We want to improve the resilience of systems, right? Whether that's agricultural systems, whether that's hydrological systems, to what's coming. Okay. And it costs money, right? And the idea, though, is that this may be money well spent. So one thing that we have certainly seen here is the simultaneous drought flood challenges in California. And this is part of the California story, but climate change is certainly exacerbating the problem. How do you plan for both climate change, or how do you plan for both drought and flood? Right? That is one of the challenges that I know the water managers are dealing with quite a bit. I was working yesterday with the Turlock Irrigation District. They're planning for climate change. Right? They're also planning for ways that they can store more water in the ground. And this has come up a lot in the news recently with the crazy amount of precipitation we've had here. You've seen a lot of standing water, right? We know there's a lot of water that has been taken out of the ground here in California. In fact, over the last 20 years, the amount of water that's been removed from our groundwater here in California equals the entire surface reservoir capacity of the state. That's how much is now gone, taken out of the ground. Okay, so we need to do something to put more water in the ground. Recharge is what all the buzz is about now. How to do that at large scale? I don't know. It's hard to do, right? It requires a lot of effort and coordination. I know that yesterday when I was with the Turlock Irrigation District, they estimated that within their territory, they could actually put around 800,000 acre-feet of water into the ground per year. That water by itself would be more than sufficient to supply all of the agriculture in their district. Okay, they're primarily relying on surface water. They're pretty water rich right now. So groundwater is certainly the way to go. How to do this fast enough, I don't know, because we only get these wet events every 4 or 5 years. So we may have to wait again quite a while to get another, crazy deluge like this. At UC Merced, we are working on this issue. We've got a couple grants to look at how to couple climate measurement and management to improve the water security of agriculture in the Central Valley, along with in Utah and New Mexico, all these semi-arid areas that are dealing with water scarcity. We're trying to work on different technologies to ensure that these agricultural communities can continue to thrive even with climate change. Okay, there are a lot of opportunities out there. It's a challenge to move the needle, but we're beginning to work with growers on how to use this information and make better decisions. The last piece here is mitigation, right? So carbon being put up into the atmosphere didn't show up that well, but basically we have fluxes going into the atmosphere from a variety of sources, right? And we have only so much going out of the atmosphere. So this is my bathtub analogy. We have too much going in, not enough going out. The bathtub is rising, rising, rising. The goal here is to reduce the amount coming in or to increase the amount going out, to lower the level on that bathtub. Okay, so this is a harder one to do. Adaptation can be done locally. You all can adapt to climate change right now if you wanted to some degree. Mitigation's hard, right? And this is a global problem. Climate change is a global problem. Carbon dioxide remains in the atmosphere for 20 to 100 years, right? So it's a bigger challenge to deal with. The middle panel looks funny, but look at the other side. So this figure here I think is instructive to sort of highlight the challenge and possibly the urgency of this challenge. So on the x-axis, right, we have total amount of carbon, CO2 emissions since 1850, right? So each time I drive my car back to Fresno, the needle starts moving further to the right here, right? And then on the y-axis, that is the amount of warming globally since 1850. All right? So warming globally generally relates relatively well to the amount of cumulative carbon dioxide emissions from humanity. There are these sort of goals here of slowing down the amount of climate change such that we do not reach more than 2 degrees Celsius globally above pre-industrial levels. Okay? It's a bar. It may not be the bar or the only bar, but it's a bar. So let's show you where the bar is here. So 2 degrees Celsius, right? And then there are projections. Those different trajectories show you projections, right? Uncertainty in how we're going to use carbon dioxide, population, sharing technology. We don't know what's going to happen. But the nice thing is they all sort of follow that same line. And so from that, you can get an estimate of how much more carbon dioxide we have to emit before we reach 2 degrees Celsius. And the answer roughly is that we have about 1,000 gigatons of carbon left. Sounds like a lot, but if you do the math here on how much we're emitting each year, right, and assuming no more increases, we've increased the last few years after COVID, you can kind of do the math, right? It's how many years we have left. So this is the urgency here of mitigation. How do we do mitigation? Lots of ways, right? These are 3 ways that I think are manageable in chunks, right? You can't solve this entire problem of mitigation with one silver bullet, right? It's like buckshot. So one is to move to electrify as much as we can. And And that works fine, right, as long as you have energy sources that come from non-fossil based fuels. So it works pretty easy in certain states, like the Northwest, where they have a lot of hydropower. It doesn't work really well in places like Ohio and West Virginia, where they're primarily, coal-based. Okay. So the second piece here, and we're moving this way, right? You can look at the number of electric vehicles on the road, and there's some crazy statistic like the number of electric vehicles, that come online this year in the U.S. will equal the total amount that were online in the previous several years. Right? That curve is dramatic, and I'll show you that here in a bit. Decarbonize the grid is the next piece. That's harder. We're paying for it to some degree with higher energy costs. The upshot is that if we pay now, we maybe avoid costs later. Okay, and this is part of the Biden's administration's goal, a little bit part of the IRA, right, to move to 100% net carbon-free energy by 2035. Some states have a much easier time getting there than others. I don't know the portfolio in California off the top of my head, but we certainly have a lot of solar. We certainly have wind. And our reliance on fossil-based fuel is declining. The other piece is agriculture. So back to agriculture, pretty topical here. Agriculture is a significant contributor to greenhouse gas emissions. Right? It's especially with things like fertilizers. That's a big player there. Obviously, these things improve the yield per acre. Okay, so part of the challenge with solving agriculture and solving food is that we have a growing population, and the population is eating a more protein-rich diet too. So this is one of the grand challenges of how do we feed the world with a finite amount of land and reduce our carbon emissions from agriculture. But with each of these, right, they all look like big challenges, but they all have potentially big payoff, not in terms of just the climate change benefits, right, but also economic benefits for those who figure out how to do this and scale it. And so I will show you this graph here, which shows us progress. We have made progress. We'll just focus on one of these. You can see the solar, right, photovoltaics. It's a hard one to say. PV, that's why they put that up there for me. Look at the cost of solar power, right, in 2000. It was super expensive. See the gray line there? That gray line there is the cost of essentially fossil fuels. Fossil fuels from energy was much cheaper in 2000. Today, solar is extremely competitive, maybe even cheaper than fossil-based fuels, right? You can kind of see this portrayed across different elements here. Likewise here, the adoption of electric vehicles, that looks like a hockey stick to me. In the realm of climate science, we think of hockey sticks as being rising, escalating global temperatures. This is a good hockey stick in terms of at least beginning to rely less on from gasoline, right, internal combustion engines. We have to be sure that that energy is coming from non-fossil based fuels. And then there's this, and this was actually, I think this is actually in Modesto. Yeah, so I mean, what's more American than this? A giant semi of chips, but it's powered by an electric vehicle. So this is a paradox that we're seeing, where we're seeing things like GM and Ford, who 10 years ago had zero interest in this, are now leading the charge. So I think there is some room for optimism. The time is ticking with climate change in terms of some of the bars that have been set. We're beginning to sort of change that trajectory. And at the same time, we're seeing the impacts mount. So that's essentially what I have. We have bad news, we have good news, but hopefully we have some good news that we all can leave with. And I'm happy to end there and field any questions folks have.